Hi, I'm Justin Hansen, and today I'll be going over assignment 2, in which we, in class, created MATLAB code to define the position of an end effector of a robot that is a revolute, perpendicular to revolute, parallel to revolute robot. Um, in class, we created these homogeneous transformation matrices, and to compute the forward solution or the forward kinematic solution to this, we take the robot's link length, which is 107 millimeters height for the base, 150 millimeters for the length of each arm, and then to find the position, we input each of these into the homogeneous matrix. Or we don't input these into the matrix, just the matrix puts out, let me run it. It puts out these position values. This is the x, the y, and the z position values of the end effector after um, after each transformation. And once we have these, we plug each length value into each equation, as well as plug in each theta value into it. And we find the position of the end effector according to these theta values and the lengths of each part of the robot. And so after completing the forward kinematics, we complete the inverse kinematics, where we want to find the angles of each rotation for the base rotation, the first arm rotation, and the second arm rotation. That would get us to that end effector location. And so we just use the solve function and put in the position values we found from forward kinematics, as well as the theta values we used. We input that as our initial guess, and then the output will give us the degrees for each theta value that would get us to the position that we found through the forward kinematics. And so I put in 0, 0, 0 for the forward kinematics, and the solution for the inverse kinematics gives us 180, 180, 0, or 0, 0, 0, which means that I could have placed 180 in the first and second theta values, and we would have gotten the same location, which was 300 in the x and 107 in the z millimeters. After completing the kinematics, we want to create a robot that is defined by those kinematics. So I create the robot, I create the base, the arm, the second arm, and the end effector, which is a suction cup in this case. And for this, in the kinematics, I defined the base as 107 millimeters high, but in this robot, I define it as 87 millimeters. And this is because I want there to be an air gap in between the base and the arm so that they don't collide with each other. And so I place the air gap right here when I am putting the objects together, when I'm assembling the whole robot. And so I also define the arm the same way. I have it 20 millimeters less than it is in the kinematics. This way I can have an air gap between each arm so that they don't collide with each other either. And the sphere I place inside of the second arm. That way, when we find an end of effector location, it is touching the tip of the second arm. After that, I set the base in its position, which is just at the origin. I don't do anything funny with that other than set its rotation around the global z. For the first joint, which is the arm, I set its rotation around the global y because I don't want it to rotate the same way as the base does. Instead, I want it to, as we found through hand performing the inverse or forward and inverse kinematics with the homogeneous matrices, I want it to rotate around its local z, which for the global environment, it would be the global y. And then in order to make sure that it is perpendicular to the base, I have it rotate 90 degrees around around the y-axis. Joint 2, I do much the same as joint 1, except I have that air gap, so I have a 20 millimeter space between the two. And then the suction joint, I just place at the very end of the second arm. Finally, the robot's assembled, and the robot is here. And this is the robot that was made based on the kinematics we did in class. Finally, with this, we want to go to the KinematicsDesigner, which is around here. And so now with the InverseKinematicsDesigner open, start a new session, open the robot that we just made. Here it is. And now we can tell it to move to different locations. And so what we want to do first, just to test if the kinematics work properly, our first solution to the kinematics, we want it to be 0, 0, 0, so find its home location. It should be at 300 millimeters in X and 107 millimeters in Z. And so if we go to the designer and we edit the constraint for the target and put this at, oh, it's already there because it's at the origin, at home, and that's exactly what we wanted. And so now we can test another position in order to see if the kinematics are accurate or accurately describe its positioning. And so we can have it point straight up, which this code should do because I have the first joint or the first arm rotate 90 degrees, so it'll point vertically. So it's estimated that it'll be 0 in X, 0 in Y, and 407 in Z. And so if we test that, all we need to do is change the Z to 407 and change the X to 0. Apply that. Oh, we also have to change orientation weight to 0. And there we go. So now the robot is pointing straight up, and this green check mark means that it did reach there. And that's exactly what we wanted. And finally, just for another test, we can try moving it to 30 degrees for the first arm and 50 degrees for the second arm. Now it's estimated that this will get us to 270.8 millimeters in the X. So 270. We'll say 86 in the X, or 270.86. And then in the Z, it should put us at 130.69 in the Z. So I'll do 130, and that's more like 0.7. So I'll do 0.7. And we apply this. And this is one of the rotations. I'm not a huge fan of that one, so I'll manipulate it myself to get the more likely one that the kinematics find. Be right back. And so now it is in the position of 270.86 and 130.7, like we wanted it to be in. And this is just a more likely position that that our kinematics, or that our robot would go to if we wanted it to go here. And so if you look at each arm, if it's at 0, it'll be along here, which is actually 90 degrees for the global environment, which means that this being at 60 is 30 away from the global environment's 90 degrees. And now this arm being at 70 means that it is 20 degrees from the environment's global y axis. And you can tell that it's correct because 60 degrees right here is 30 away from 90. And then going in the other direction, you would go back to 90, which is 30, and then 20 more, which is 70. So this is 50 degrees away from the first arm, which is exactly what we want. We want it to be 30 degrees and then negative 50. Uh, this negative should probably be inside of here just to be more clear, but it is 30 degrees and negative 50 on the in the inverse kinematics. And so after that, we just want to show, or our assignment wants us to show the workspace analysis, which shows every location that um, okay, and we're back. Sorry, the robot's type was struct and not row, so I had to go back to the my file where I made the robot and turn it into a row formatted robot to match with how the workspace analysis kind of um, configures or manipulates the robot. But after creating a custom index and generating the workspace, we can find uh, that the custom index gives us this kind of view of the robot, showing each different location that it can go to, where it can go to well and where it might not be able to reach. The orange is where it's harder to reach, or the red in this graph's case, but the blue is where it can easily reach, and the light blue is where it's less likely to reach, and same with yellow, even less likely. Um, the second graph is the non-voxelized version, and so what the voxelized version does is it just takes uh, all of the points of data that it tries to reach and kind of compresses them into more localized, more locally distributed, or a more even spread around the whole environment. But the voxelized just shows every single test that the program went through to try and see where the robot can and cannot reach. Um, and so again, the dark blue is where it's easy to reach. The red, which is almost all in the center, is where it's hardest to reach, and also along the outside. Um, but yeah, this is just showing the kind of environment that you have available to you with this specific kind of robot. And um, it's helpful to be able to see the kind of space that you have available or that you have available to work with for your specific needs. Um, Aside from that robot, I also made another one that more accurately depicts the Doobot using class. It is made to be more similar by starting with this kind of orientation, and it also has the end effector located down here instead of connected to the second arm like it was previously. Um, all I had to do for this was create another kind of block here to allow the end effector to be connected down here. And I just did that by making another collision box. I made it 0.2 out because the tip of that of this new box will also have a 20 millimeter gap, so it'll be or it'll be 40 millimeters away from the second arm. So the distance, the perfect distance for the end effector to go down. And um, it didn't really need much changing. All I did was include the third arm here when I was adding the body, make sure I created a visual form of it, and the suction joint. Yeah, I just changed it to be 0.02 out because now that it starts a bit further, it doesn't need to be the 0.04, the full 40 millimeter distance, but it is still the full 76 millimeter distance down. And that came out to look like this right here. where you have the base, you have the first arm, second arm is 25 up and 50 millimeters in the X away from the initial arm. The tip of the new box is 40 millimeters away from this arm, and this ball, the center of it is lined up with the tip of the base of the end effector, and so it is positioned um, exactly where it needs to be for it to model this diagram. And that is evidenced by the InverseKinematicsDesigner, where you can see this is the model, and I'll make it a bit larger. When this is at 0.24, 0.206, that is the proper distance for this by adding up all of these lengths and uh, finding this position. It is the proper, it's in the proper position, and when you look at the angles of these, they're both at 0. This is plenty close enough, and this is 90 degrees because it is in relation to the y-axis of this whole thing, or in relation to the z-axis, it's 90 degrees from that. And you can move it just fine to get to every location on in this space. When comparing my doobot to the simulated doobot that we have in the doobot lab app, we can find that from its home position of 240 and 145, I had to change my code a little bit to make this fit by having the base start 61 down. That way it had the same origin as the simulated doobot. But after doing that and telling the doobot to go to a certain position, 260, 50, I find that their joint angles are 18.63 and 35.52. And I look at how mine does at that spot. See, it's 0.26, which is 260, 0.05, which is 50. My first arm is at 13.48, which is about 5 degrees off of 18.6. And then my second one is at 62.46, but it's in relation to the horizontal y-axis, or the x-axis. It's from the x-axis down, and so it's about 28 down compared to the 35.52. So it's off about 5 degrees and 7 degrees for both, which is likely due to this space right here. Just such a large gap that has both a translation in the z and in the x that is causing some kind of smaller error. But it isn't too different as to where like it would be a totally different robot. And after performing the workspace analysis for this robot, it comes out to look like this. Very similar to the previous one, but definitely just a larger larger area, a larger sphere that's created, and possibly more red, more unreachable spots, but overall there's more area that it can reach. And that is it. Thank you.